All right, welcome back, guys. All about chemistry, biochemistry. Once again, I am Dr. DeChavo. Going to be going through chemistry today. Now, the thing about this lecture, it's not going to be as exciting as that rock show. I wish. I wish I could sing. I would sing on my lectures too, but I can't, so I won't, because you don't want to hear me sing. So, we're going to be going through chemistry. This is a little tough. The thing about these chemistry lectures I explained to you in the last lecture is that I'm trying to take bits and pieces of what you'll need in the future without covering everything. So if you just came out of chemistry, you're going to say, wow, this is just, spotty little explanations here and there. That's because you only need small amounts. If you haven't had chemistry recently, don't panic. Try to listen to what I'm telling you. If you understand at least 50 to 60% of it for now, I'm good with that, okay? And of course, if you have any questions, shoot me an email. Let me know if you need to meet with me. I'd be happy to meet with you, whatever it takes, okay? So let's start with, I'm going to zoom you in so we can look at this, biochemistry, okay? Once again, reflecting my taste in music, 80s, 90s, early 2000s, okay, semisonic chemistry. So biochemistry we're moving into. Biochemistry is the study of chemistry, is how it relates to the body, okay? If you don't remember this, there's organic and there's inorganic. One of the major things is that organic chemistry is going to have carbon. Inorganic can too. But what generally happens with organic is we'll tend to have longer chains of carbon or more complex structures with carbon. Inorganic tends to be salts, acids, and bases. Okay. Organic is going to have covalent bonds, so there's not going to be that charge. Inorganic, a lot of times, will separate out into ions. Okay, we'll have that sodium chloride that'll dissociate into a positively charged sodium and a negatively charged chloride with inorganic, for example, okay, just as an example. And of course, there's crossover, but these are general terms for the two. Okay, so inorganic compounds we're going to go through first, those salts, acids, and bases. Once again, this is not to teach you chemistry. This is to teach you the amount of chemistry that we need to know that applies to our class. Okay, so water. Water is going to be a molecule that's super duper important in the body, considered in this grouping because it's not going to be long changes of carbon. It's a smaller molecule. And a couple things make it a very important solvent for our body. Okay, that's why it makes up 60 to 8% of the body's composition, because it's so important in these chemical reactions. It holds heat. Okay, it has it has to be heated up in order to break its bonds, so it can actually pull heat away from the body. Okay, it takes heat away from the body. That's why we sweat. Water gets onto our skin. The heat from our body gets pulled out of our body because those water molecules take a high amount of heat to break them apart. Okay, why does dirt come off with our skin and water? Remember that polarity of water where the oxygen is going to have a slightly negative charge, the hydrogens are going to have slightly positive. That polarity, that charge actually pulled dirt off the skin. And why is our brain floating in our skull? Cerebrospinal fluid helps to provide a thin layer of fluid that helps to cushion the brain and the skull. The brain, guys, has the consistency. If I were to take your brain out and poke at it without preserving it, okay, when we look at brains in the lab, either sheep or human, if we go on the cadaver trip, the brain, it has the consistency of a really thick pudding. Okay, it's not very hard, and it's sitting in the nice hard skull to protect it. But if we were to whip your head around, we'd be banging that brain, which is the consistency of thick pudding, around inside your brain. You bruise it. Okay, this thin layer of cerebrospinal fluid, which is mostly water, is going to help to cushion the brain. Salts, where's the fries? So salts, as I said, are going to be chemically bonded molecules that can form electrolytes or charged atoms. Okay, so electrolytes are charged atoms. So a lot of these chemical structures, and I have examples listed below, We can ingest them, such as sodium chloride, and they'll dissociate into ions. Now, the two on here, we're not really going to get into many of these. The two in here that we're really going to get into is going to be sodium and potassium. Okay, so sodium chloride and potassium chloride will dissociate once we eat them in our foodstuffs or ingest them into a sodium and a potassium ion, which are going to be both positively charged ions, which are known as electrolytes. So if you were to go out after this class, run a mile, 2 miles, 5 miles, whatever, and you need to replenish your electrolytes, what you would be doing is ingesting primarily sodium, potassium, and calcium in those electrolyte drinks to replenish your electrolytes, okay? And they're important. These electrolytes are going to provide several physiological functions. Two of the big ones, just to give you an idea of why these are important, two of the big ones that these electrolytes help to provide functions for are the firing of nerves and the contraction of muscles. Okay. So acids versus bases are going to be important to know as well. Acids and bases are electrolytes. An acid gives off a hydrogen ion. So here's another ion that's going to be important for us to know. A hydrogen ion is going to have a positive charge when dissolved in water. Okay. When we have a solution that is acidic, it would taste sour if you were to taste it. If we were to have a solution that was more basic, it would be bitter. Okay. Acids are proton donors. They will take that hydrogen ion and want it to latch onto somebody else. Okay, it's going to want to attach to something else. Quite often, but not all the time, when we're looking at acids, the H or the hydrogen will be written first and the group after, and then there will be a group after it. So hydrochloric acid will be written as HCl. That would dissociate into a hydrogen ion with a positive charge and a chlorine ion with a negative charge. Okay? So acids are sour, proton donors. They will release hydrogen ions when dissolved in water. An example would be hydrochloric acid. Now, bases would taste better. We talked about that. Now, they're proton acceptors, okay? If you look at it, when we have a base put into our body or into solution, it will release what's called a hydroxyl group, okay? And that's going to be OH negative, okay? Now, I want you to look at that OH negative, and then I want you to look at the hydrogen on the left side and think possibly what might happen when they bond together. We're going to have now two hydrogens. They'll eliminate those charges. They'll neutralize those charges. We'll have H2O, okay? So acids and bases, when bonded together, will form water. What happens in solutions, though, is if we get too many bases, we can't neutralize them. It becomes more basic. In an acidic solution, if we get too many hydrogen ions, it'll become acidic, and we can't neutralize it, okay? So if we have equal amounts of both, they'll neutralize each other. It's when we get too many of one or the other that we get too acidic or too basic, okay? So sodium hydroxide is an example at the bottom there. Once again, we're not going to get really into these. I want you to understand the concepts, okay? So sodium hydroxide will dissociate and give us a sodium ion and a hydroxyl group. Okay, OH negative or hydroxide, hydroxyl ion, whatever it is that you want to call it. Okay. So pH is going to be acid-base concentration. It's all about the concentration of hydrogen. So the more, it's not about hydroxyl groups, it's relative to how many hydrogen ions we have. The more hydrogen ions, the more acidic, the lower the number. It's on a scale of 0 to 14. Okay, 0 is going to be really acidic. 14 is going to be really basic. 7 obviously will be neutral. Cool enough, it was created by a Danish biochemist who was also a part-time beer brewer who was trying to figure out how to regulate the taste and the bitterness of the beer. And he actually developed this pH scale. So he was able to monitor that acidity in beer. I don't know what the acidity in beer is supposed to be. If anybody knows, let me know. That'd be kind of a cool thing to know. Okay, so he monitors that acidity, and it helped to make the beer taste better. Okay, so here's the pH scale. I have two examples in there. Okay, you can see on the right side of the scale is the measurement of those hydrogen ions, excuse me. Okay, and it's measured exponentially. We're not even going to get into that. Okay, we're just going to worry about the 0 to 14 scale. 0 being acidic, 7 is going to be neutral. Make note, there's blood right in the middle there. Okay, there is a very narrow range for the level of acidity for blood, 7.35 to 7.45. We need to keep it in that range. Okay, and then sodium hydroxide is going to be very basic at the opposite side. But we need to keep things neutral. Okay, don't think of acidity being bad and alkalinity, or alkalinity is another word for being basic, is being good. That's not the case. Neutral is good. Being too basic, which would be close to 14, or too acidic, which would be close to 0, is bad for the body. We want to be right in the middle. Okay? Now, we can have neutralization reactions. Remember I mentioned when we're talking about acids and bases, if we have too much acid, that's bad. We can't neutralize it. If we have too many bases or too much of a base in our solution, we can't neutralize that. But if we have an equal mix of an acid and a base, it'll actually form water and a salt and neutralize that acidity and that alkalinity. Okay, so if you look at that equation there, there's a strong acid, which would be the hydrochloric acid, and a strong base, which would be your sodium hydroxide. Those will actually mix together to form H2O. The hydrogen and the hydroxyl groups will combine. Okay, so that acid and that base will combine, the hydrogen and the hydroxyl group, the OH, and form H2O. Then the sodium and the chloride are left. They form together, or chlorine, I'm sorry, I was getting those transposed. Sodium and the chlorine come together and form sodium chloride. You get very basic salt water, okay? So neutralization will form water and a salt, and will buffer those, not buffer, I should say, will neutralize the acid and base, okay? I said not buffer because here are systems that will actually buffer, okay? We need to make sure that in our blood we have a range. So see that 7.35 to 7.45. Please put next to that this is in the blood. Okay, 7.35, 7.45. This is in the blood. It's very important that we keep within that range or we will die. If we become too acidic or too alkalinic, we will die. If we have a strong acid that we ingest, will release too many hydrogen, okay? And we can become too acidic. If we have a strong base get into our system, we'll release those hydroxyl ions, and we could have problems then. So it's got to stay, remember, this is in the blood and the interstitial tissues. I'm not talking about like the stomach or the intestines. This is within the blood, okay? We need to maintain this range. So there are systems put into place called buffers, which help to maintain this. So our body's constantly monitoring, looking out to see if there's huge changes in pH, and these buffers will pull into play. It's the kidneys, primarily, the lungs, and the blood, okay? I'm gonna bring you out because I wanna talk to you about this, okay? So kidneys, lungs, and the blood. So these are buffer systems. Okay, just some basics. We're going to actually go into these in the future. So your kidneys, guys, your kidneys actually will release hydrogen ions or retain them in order to buffer our system. They also will release bicarbonate ions. Now, what do we use bicarbonate for? We can actually buy bicarbonate. You can take a teaspoon of bicarbonate and eat it to help calm down an acidic stomach. Bicarbonate is a basic or alkalinic substance, okay? So in the kidneys, we're going to either release or retain hydrogen ions or release and retain bicarbonate ions. So those hydrogen ions are going to be acidic, and bicarbonate is going to be basic, okay? So our kidneys can either release or retain hydrogen ions or release or retain bicarbonate, depending on what's going on in our system. So if our body senses that we are too acidic, our body will release hydrogen ions into the urine, and it will retain bicarbonate ions. If our body senses that we are too basic, it will release bicarbonate ions and retain hydrogen ions. So these two substances actually will be opposite each other, okay? They will release one and retain the other and vice versa. So one more time, the kidneys help with buffering our system as a whole to maintain that pH of 7.35 to 7.45. If we become too acidic, okay, so our body is becoming too acidic, we need to get rid of some of that acidity. The hydrogen ions will be dumped into the urine. We will retain bicarbonate to help to absorb some of that acidity. Okay. If our body becomes too basic, our body will get rid of those bicarbonate ions and retain some of those hydrogen ions. Those hydrogen ions can join or absorb some of those basic substances in our body and form the basic water and salts, okay? So it's kind of a counter-current mechanism, per se, okay? So kidneys. Lungs. The only substance that we will deal with in the lungs when it comes to acid-base is going to be carbon dioxide. Put this in your head. Carbon dioxide is acidic. Okay? Carbon dioxide is acidic. That is the only thing we're going to talk about in the lungs. So if the body becomes too acidic, we will start to blow more carbon dioxide off. This is the whole basis behind that breathing change with diabetics. We'll get into it in the future, called ketoacidosis. So lungs, the only thing you need to remember in the lungs is carbon dioxide. If you become too acidic, you'll blow more carbon dioxide off. If you become too basic, you'll actually slow your breathing mechanism. Okay? And blood. The blood buffer I'm going to talk about in the notes because we need to look at this. So buffer systems include kidneys, lungs, and blood. If the pH changes too much in our body, we'll use the kidneys, the lungs, and the blood to help balance that pH with these buffer systems. Okay? If you don't get this, come see me or send me an email. Okay? What I would do is study it for 10 or 15 minutes, rewind the tape, and watch it again. Okay? So buffer systems, kidneys, lungs, and blood. So I'm going to zoom you back in and talk to you about a few more things. Okay? So buffers help to maintain homeostasis, balance our system to keep it within 7.35 to 7.45 range pH. Kidneys, lung, and blood, I would write blood above chemical systems, help to maintain this balance, okay? We're going to have a release of hydrogens from strong and weak acids. You know what, you don't have to really get much into this, but I want you to understand a little bit of the concept. Strong acids will release a lot of free hydrogen. Weak acids release fewer hydrogen, okay? And can actually revert back to a buffer system. We'll get into that in a little bit, okay? So strong acids are going to release more hydrogen. Weak acids release fewer. Okay? This, guys, is the buffer system that we will see in the blood. Okay? It's called carbonic acid-bicarbonate system. It's just chemicals that exist in your blood that help to buffer these free hydrogen ions, okay? Carbonic acid is H2CO3 that you see at the left of the screen. It's a weak acid. When we have that in our system, it has minimal to no effect on our pH. So don't get confused by it saying it's a weak acid. Okay, it has minimal to no effect on our body when it's in this form. You with me? Okay. When we have it convert to bicarbonate, okay, we'll have a bicarbonate ion, which is HCO3 negative. Okay, so H2CO3 is going to be a weak acid. HCO3 negative is bicarbonate. Okay. It will release bicarbonate and a hydrogen ion. Okay. Now, what happens, you can see the arrows there, is in a response to a rise in pH, it'll move over to that right side, the bicarbonate and the hydrogen ion, okay? That bicarbonate will then actually be able to accept or buffer some of those hydrogen ions, okay? If there's a drop in pH, okay, if there's a drop in pH, it'll become more acidic and it'll move to the left there, turning into carbonic acid, okay? So carbonic acid bicarbonate system, okay? Don't worry too much about this. Just understand that carbonic acid bicarbonate system is a buffer system that exists in the blood, okay, that will help to resist pH changes. And it can move to carbonic acid, which is a weak acid, or it can dissociate and release those hydrogen ions and move to bicarbonate on the right, okay? So, carbonic acid, this is really what I want you to worry about, okay? That last picture gets very confusing. I want you to understand carbonic acid bicarbonate is a chemical blood buffer that's a reversible equation that helps to create balance in the blood, okay? It keeps it within that normal pH of 7.35 to 7. Let's go with 4.5. I have that in the notes, but let's go 7.45, okay? Bicarbonate is HCO3 negative. Carbonic acid is H2CO3, okay? Normal PCO2, so this is going to be the pressure of carbon dioxide in the blood, is 35 to 45 millimeters per mercury. It's just kind of a number that you should start to get familiar with, because if you start to get too much CO2 in the blood, you get too acidic. So if you go above 45 millimeters per mercury, you become too acidic. If you go below 35, you become too basic. Okay, so normal CO2 is a kind of narrow range, really. And this will change if people have lung problems. Okay? Okay. So, abnormalities of acid-base balance. The thing that you really want to focus on with these abnormalities of acid-base balance is going to be kidneys and lungs. Okay, it's going to be kidneys and lungs. So I want you to think, I want you to pause the tape. I'm going to move on. I want you to pause the tape and really pretend like we're in class and you're thinking about this. And I'm going to ask you a question about this. When do these problems occur? So if a patient is not in normal pH, and they have either acidosis or alkalosis, and alkalosis means they're too basic, when would this happen? So when would respiratory acidosis happen? Respiratory acidosis means that for some problem we're having in the lungs, we are becoming more acidic. So you want to ask yourself, is this patient retaining too much carbon dioxide? And once again, carbon dioxide is what? Acidic or basic? It's acidic. So they're retaining too much carbon dioxide. They are going into respiratory acidosis. because they can't get rid of that carbon dioxide. An example that this would happen in is somebody who has emphysema. Okay. On the opposite end, respiratory alkalosis is when the levels of carbon dioxide are too low, and that patient is probably hyperventilating. Okay, and they're getting rid of too much carbon dioxide. Now, metabolic acidosis is going to deal with the kidneys. So metabolic acidosis means that there is a problem with the kidneys that is making us too acidic. In that case, the kidneys have a disease process that are making them retain too much hydrogen and probably get rid of bicarbonate. Okay, because don't forget, kidneys are going to be the metabolic buffers. They're going to deal with hydrogen and bicarbonate. Okay, so they're retaining too many hydrogen, they're getting rid of too many bicarb. Now, metabolic alkalosis is going to be the opposite, a disease process in the kidneys that will cause the kidneys to retain too much bicarbonate and get rid of too much hydrogen. Okay, so you got to, once again, write down what substances affect them and kind of look at it and think about it, and then watch the tape again. Here's an explanation of each one. This is what we just talked about. Okay, whether it's acidic, whether it goes alkalinic or alkalosis, what the change in pH will be, and some examples of how that can happen. Okay. Physiological effects of acidosis and alkalosis. Less than 7 can cause coma and death due to central nervous system repression. Greater than 7.8 is overexcitement of the central nervous system. Tetany is almost like a reflexive kind of contraction of the muscles. Okay, tetany. Like a tightness to the muscles, nervousness, and convulsions. Okay, eventually leading to death from respiratory arrest. So that's a pretty narrow range, isn't it? 735, 745. Okay. Organic compounds. So we are going to do, a couple more slides talking about carbon-containing compounds. Don't forget that inorganic compounds can have carbon as well. It's how the different bonds are, okay, that make a difference. And the fact that inorganic compounds can form water and salts, okay, and acids and bases. So organic compounds are going to be carbs, lipids, and proteins, okay? Unique to living systems. Oh, there it is right there. Carbs, lipids, proteins, and nucleic acids actually are in there as well. Okay? Many are polymers, which means that they are chains of similar units. So what happens is these small structures, for example, glucose is going to be an example of an organic compound, okay, is going to be linked together with other glucose units and other structures as well to form long chains of similar units, okay? The way that they're put together, and I'm going to bring you out because I have a silly little way to remember this, okay? Whoops, that's the wrong one, sorry. Okay, I have silly little way to remember this. I had the hardest time remembering dehydration, synthesis, and hydrolysis. These are going to be the chemical ways by which we either put these units, for example, 2 glucose units together, or we break them apart. Now, don't forget, as we're talking about these organic compounds, they don't have a charge. So if you break them apart, they would have a charge unless you add a water molecule to them, okay? If you're putting them together, you'll take a water molecule away, so now you can put them together and not change the charges. It's way more complex than that, but that's the basics of it. Okay, so they don't have a charge or need a charge, so we use water to either take it away or put it together, okay, to either form bonds or break the bonds apart. Confusing, right? So I have a simple way to remember this. Dehydration synthesis. You'll remove a water molecule in order to bond these 2 structures together or molecules together, right? So we stick them together. And I always remembered when you're dehydrated, I can't believe I'm doing this on tape, your You stick your cheeks together because your mouth is so dry. So dehydration, synthesis, you're removing water so you can stick these molecules together. Stupid, but if it helps you remember, great. Okay. Hydrolysis is going to be the addition of water to break the bonds apart between these two molecules. The way I was thinking of it as I was preparing the class years ago is I was walking down the stairs right over here near your lab, and there were two students basically making out on the couch. And I just wanted to take a big fire hose and add water to them to break them apart. Okay? That would have been hydrolysis of those two students. Hydrolysis is the addition of water to break the bonds between molecules or students. It's your choice. Okay? So, dehydration, synthesis sticks molecules together. Hydrolysis is the addition of water to separate them apart. Okay? So, I have a video for you for dehydration synthesis. I'm going to zoom you in. Okay? And play it. I guess there's no sound. Okay, so let me back it out and animate it for you really quickly. Okay, so we have two basic sugars, okay? Glucose and fructose. We remove a water molecule, okay? There's water, and now we form sucrose, okay? Okay, so basic animation. So let's get back to the PowerPoints here. Dehydration synthesis, the removal of the water to stick those two molecules together. If we want to break the bonds, we're going to add water to take the place of those broken bonds. Okay, so I don't know if this picture helps you. This is an old picture from the book of dehydration synthesis. At the top, you can see the removal of the water to form two units linked together. The next one down is going to be the addition of water to break the bonds between two covalently bonded molecules. Okay. The bottom is an actual presentation of the chemical structure of glucose and fructose being bonded together to form sucrose. These are all sugars, okay? And then it shows it's a reversible reaction, so it can go back and forth. Okay? So now getting into carbohydrates. Now remember, carbohydrates are basically, they form some little bit of structure of the body, but primarily it's going to be used, or they're going to be used for energy. They include sugar, starches, and fibers, okay? They have carbon, hydrogen, and oxygen in their chemical makeup. The most basic sugar is a monosaccharide. I'm kind of going through this quickly because I think this is easy. Please redo the tape if it's too fast. Okay, so simple sugar, for example, is glucose, galactose, and fructose. Those are all monosaccharides. Mono meaning one. Di is obviously going to mean two. These are two monosaccharides that are linked together. Okay, sucrose. Fructose and glucose is going to form sucrose, and sucrose is our table sugar. Lactose is going to be glucose and galactose linked together. Maltose is going to be glucose and glucose linked together. Maltose is beer sugar. Okay, lactose is going to be milk sugar. So these three are going to be slightly more complex, but they're only going to have two monosaccharides. Now, when we get into polysaccharides, these are going to be long chains of sugars. These could be as long as hundreds of sugars linked together. These are going to be starches, fibers, and glycogen, okay? And they're going to be multiple monosaccharides linked together. Okay? Examples of monosaccharides, I'm not going to get into the chemical structure. So as you're looking through this, I just like to put a lot of visuals. Different people learn different ways. Okay, what I tell you and lecture to you is what I want you to know. Okay, so monosaccharides are going to include those glucose, fructose, and galactose molecules. They also include deoxyribose and ribose. And if you think for a minute, those are found and DNA and RNA. How cool is that? So DNA and RNA is partially made up of sugar. Okay, or monosaccharides. Disaccharides, here's that sugar, maltose, lactose. Sorry, I forgot to put that animation there. So if you try to look at the animation, I'm sorry, it doesn't link in anymore. Okay, so sucrose, maltose, lactose. Polysaccharides are going to be long, long chains. The one that we will deal with the most is going to be glycogen. Okay, glycogen is glucose, long, long, long chains of multiple glucose linked together and stored either in our liver or our skeletal muscles. Okay, that way, if we went out of glucose, our body can tap into that glycogen and can use those stored forms of glucose. Okay, lipids are going to consist, or lipids are our fats. They're going to consist of carbon, hydrogen, and oxygen. They're insoluble in water. We knew that to begin with, right? Because if we pour fat and oil together, they separate. Lipids are going to be our second most efficient way to get energy, okay? Our second most efficient. Carbohydrates are the most efficient. Energy storage, lipids, I'm sorry, are going to be the second most efficient way that we can make energy. Lipids also help us to store heat in the body. They include neutral fats, phospholipids, and steroids. Okay? Neutral fats are also known as triglycerides. They're saturated and unsaturated. So let's talk, well, actually, let me go through this and I want to show you some visuals. Okay, so saturated and unsaturated. They're in the subcutaneous tissues, which means they are underneath the skin. So when we put on weight and our hips get bigger and our thighs get bigger and our arms get bigger, it's because we're depositing these triglycerides in the subcutaneous tissues underneath the skin. Sub, below, cutaneous means skin. Phospholipids are going to have a phosphorus portion as well as chains of fatty acids, okay, and they help to make up our cell membranes. Steroids are going to actually have ring structures, or two complete rings and a half a ring joined together. You don't need to know that. That will form the basis of cholesterol, bile salts, vitamin D, sex hormones, and adrenocortical hormones, which we'll get into in the future. And then others, vitamin A, E, and K. Eicosanoids are actually fats that are stored in cell membranes that release prostaglandins, leukotrienes, and thromboxane. Those three chemicals are important in inflammatory processes, allergic responses, some contraction of smooth muscles. Okay, so they're released right from chemical cell membranes. They provide our immediate response to injury in the body. Okay, provide a lot of different functions. And lipoproteins are going to be really important, your HDL and your LDL. HDL and LDL, we know, are how we check our cholesterol levels, and they're forming our lipid panels, if that rings a bell. They're partially fat, partially protein. Okay, so if we zoom out, I'm going to show you a couple of things. So, triglycerides. I'm not going to get into a lot with the chemical structure of these. Triglycerides are going to have what's called a glycerol backbone. Okay, glycerol is going to be a sugar alcohol. You don't even need to know that much. But triglycerides, 3 fatty acid chains, will be attached to this. Okay? 3 fatty acid chains. These fatty acid chains can have a lot of different forms. There's saturated, there's unsaturated. I'm not going to really get into that, but I can if you want. I'll explain it actually next semester in metabolism. We'll get to it then. But they're going to be long chains of carbon with either hydrogen or oxygen surrounding those carbon, okay? And there'll be different length, different sizes, and different levels of saturation of hydrogen. That's where we get into saturation versus unsaturated. We'll worry about in the future, okay? So 3 fatty acid chains, triglycerides. Phospholipids are actually going to have two fatty acid chains, and then they're going to have a phosphorus. Okay, a phosphorus on the other side. So I want you to just put this image in your head. Okay, phosphorus. Phosphorus is hydrophilic or water loving. The fatty acid chains are hydrophobic. Because what happens is these phospholipids, and I actually draw them when you look at this cell membrane in next week's lecture, they look like a double-stick lollipop. So if I were to take a cell, okay, and take this portion of the cell out, and we're looking at that cell membrane, it will have several of these double-stick lollipops, okay? The head is the phosphorus, and the two tails are the fatty acids. Okay, so we're looking at the cell membrane. That round portion of the double stick lollipop is phosphorus. The two sticks hanging down are fatty acids. And in the cell membrane, we actually have two layers of this with the fat facing the inside and the phosphorus facing the outside. So the phosphorus will interact with the water surrounding the cell or inside the cell, because once again, we're made up of 60 to 80% water. And then the fat on the inside actually will help to determine what can come in and what can go out. Okay, so it helps to form what's called a semi-permeable membrane around the whole cell, with the phosphorus being those round portions and the fat being the double-sticked lollipop. So phospholipids are going to create cell membranes. They're going to be really important for creating what's called a semi-permeable membrane. Okay. Steroids we talked about, and the other ones we talked about as well. I just wanted to show you those visuals. Okay. So once again, zooming in on the screen, we've got triglyceride formation. You can see those three chains of fatty acids linking together with a glycerol backbone. Okay. Through dehydration synthesis, releasing water molecules. There is phospholipid with a phosphorus containing group, glycerol backbone, and the two fatty acid chains. Here's an example of a steroid. I'm sorry, it's 3 ringed structures and a half a ring. I think I said 2. Okay, you just need to know it's in a ring structure. Okay, we are going to take a break. Excuse me. We'll come back and finish up this chapter. This tape is getting a little bit long, so I'm going to come back here and play a little music for you, and then I'm going to stop the tape and restart it. Okay. Once again, this is a tough lecture. So if you have any questions whatsoever, I would be so happy to answer them. Write them down, shoot an email to me. Okay. Enjoy the music. Thank you so much.
This one got to number 2 and it's on 35 in the song. The Rolling Stones and Brown Sugar.